Get that out of the way, and we are good to go. Okay. All right. So looking at Google Classroom here, and Paul, so Google Classroom, once you get your login name, you're going to be able to access all this stuff and find out all the stuff that the kids are handing in and that they're doing for work. And I'll get you set up for that, as soon as you get the login. So looking at Google Classroom, you can see here on Monday that I am set to do an experiment on the Bunsen burner. All right. And you've done this type of experiment probably in grade 10. Well, maybe you didn't. I know some teachers do, some teachers don't. You go through the parts of the Bunsen burner and you get used to using it, and then we test the flame out for various different temperatures and different properties of the flame. So this is going to be our first formal lab report. Lab reports are going to come kind of in two types. It's either going to be a formal report, which involves you typing up the whole thing, and that's what I'm going to go over today. And then there's an informal lab report where it might be just fill in some blanks. That's pretty rare in this one. Or it might just be important parts of the lab where I say, today we're just going to do observations and conclusions, right? So we have formal lab reports, which are going to be, fairly beefy reports. And then there's going to be informal lab reports, which don't contain all of the particular steps in that particular lab report. What I'm going to talk to you about today is how we write a formal lab report. Essentially, really, it's how I want you to write a formal lab report. One of the most important skills that you can have when you go to university is to figure out what the professor wants when it comes to lab reports and reporting, and to give that to them as quickly as you can, right? Say your first lab, you make some mistakes, the professor kind of tells you what they want. Make sure you get to giving them exactly what you want so you don't have any, say, minus a half C or anything like that. I'm having fun here. Anyway, so you don't lose any marks, all right? And so I have a certain way in which I like my lab reports, and you're going to want to give me that particular method. You may not agree with it sometimes, but I'm the person marking, so really you got to make me happy when it comes to lab reports, and that's what this lesson is all about. Okay, so the sheet that I would have been giving you today is the formal lab report and sample document. I have it opened up here. If you've printed it off, excellent. You can make little notes on the side. If you haven't printed it off, you might want to you might want to write a note for today that's called, formal lab reports. And if there's something that maybe isn't on this page, or maybe if I say, hey, maybe you should write that down, you might want to jot that down somewhere. So if you've got the page there, you could jot it right on the page. If you don't, you might want to jot some of the stuff down. Now, this particular sheet that I use to guide you on lab reports starts with an example lab report, and the second part of the page down here at the bottom, and you'll see that this is 5 pages long, goes on to describing how I want the lab reports done. It probably makes sense to put the example at the bottom, but the way this document has kind of grown from years of editing it and changing it, we just happen to have the example at the top and then the instructions at the bottom. So I'm going to page 2 right now so that I can go over these instructions on how I want the lab reports done, okay? So I'm going to try to zoom in here a little bit because it's fairly small on the screen here. And excellent, some people are using their technology. Oh, my computer's slow, so now I'm zooming in too far. All right, back it off. This is crazy. Come on. 150? That's a little overdoing it, don't you think? That's a good one. We've got the page on the screen here. Nice. That's a lot better. Can I scroll down? Yep. This computer is an old computer, so it takes a little bit for it to get going. Okay. And as you can see, someone's logged in, which means they're just looking at it straight on the computer right now. That's awesome. That's great. Okay. So lab reports are going to be done in Google Docs, obviously, okay, because we're using Google Classroom. So it says there, each student will let's come back to this for a moment. Each student will complete a lab report using Google Docs and submit it to Classroom. Even though the labs will be done with a partner, each student is responsible for handing in his or her report that is a reflection of their individual efforts. You'll be working with a lab partner, and you'll be working as a team, all right? So when we get to the point where I'm going to talk about things like error analysis, it's okay to talk with your lab partner. What do you think the errors were in this particular experiment? But when you do that, please don't have one partner write the error analysis and the other partner copy it. Don't do that. Don't copy. But it's okay to come up with ideas together and then go on your own way and write your report. Okay? So they should never read to be the same, right? They can have the same ideas in them, but they should never read the same. You have your own writing style. I can tell whether it was a straight up copy or it wasn't. So please don't copy, all right? There will be obviously ramifications if you copy. Lab reports are to be written in third person, no personal pronouns. So that means there's no I and there's no we, all right? And that can be tricky. I struggled with that as a student. My English isn't very good, but that's the way it's supposed to be done. So when you're doing, say, the introduction or the hypothesis, please do not write I hypothesize, right? You can write it, you can write the hypothesis, or it is hypothesized, it is, and that would be fine. But please no personal pronouns. You will lose communication marks for that, okay? If you're really struggling, I came across, well, I like to read historical and old documents pertaining to science so that I can babble on and tell you stories like I did yesterday. And I came across the original documentation for an experiment that the scientist Ernest Rutherford did. It's called the gold foil experiment. We'll be talking about that in a couple of days. And I was reading through the introduction, and I could tell right away that Mr. Rutherford was not a great writer, right? Many scientists are not. And he would use a little cheat move where he desperately wanted to say I. He would put the scientist. The scientist believes. And he would then go on and continue on. And that fulfills the requirement of no personal pronouns. So if you find you're stuck and you desperately want to use an I, put in the scientist. And it makes it valid in terms of that. All right? Titles are and headings are to be underlined. This is going to be in Google Docs. Any tables that you create, also in Google Docs. You're going to notice down here at the bottom, calculations can be done on paper in the lab booklet. I'll talk about the lab booklet in a moment. And then take a picture of them. So if we're drawing images that cannot be easily done in Google Docs, sometimes we've got to draw, say, a Lewis diagram or a Bohr diagram. And that's not easy to do on the computer. I want you to do it on a piece of paper, sign your name at the bottom so that I know that it's you, take a picture of it, and insert it into your document. It's really an easy thing to do, especially with the phone. The phone is awesome at doing that particular type of maneuver, or an iPad. iPad works as well, okay? So that's the way you're going to deal with calculations. Last year I had some lazy people that didn't want to make a table. So they would make a table on a piece of paper, write in their observations, and then take a picture. Were you guilty of that? Yeah, don't be lazy. I'm not accepting laziness this year. You can easily make a table in Google Docs. So if there's observations to be done, please don't do it by hand and take a picture. The only things I'm allowing pictures to be of are calculations and various types of diagrams like Lewis diagrams. Actually, there is a beautiful equation editor in Google Docs. You could actually type in your calculations. Yes, Megan is covering her eye, but I am not going to make you do that because it can be quite tedious. But you know, I have had some students in the grade 12 type it all in, do all those calculations beautifully in there. It's beautiful. It's a beautiful document, but they don't have to be. Okay, let's talk a little bit about this lab booklet. Each student will maintain a lab booklet in which observations, calculations, etc. are kept. The lab booklet will be handed in at the end of the term. This is new. Again, as I use Google Classroom, I think of ideas that make things, I think, a little better. So we used to actually have students write their lab reports in a lab booklet like this. And now I'm going to bring the lab booklet back. This lab booklet is going to be like your observation booklet. Actually, let me show you something here for a minute. I'll track it down here if I can find it. Right here. Nope, that's not it. There it is. No, that's not it. All right. Well, that was a bust. I can't find it. I had an old copy of a lab booklet that we were to buy when I was at Western. And they're a hard copy booklet that has lined paper on one side with graph paper on the back side. And you had to purchase these for each of your science classes, because when you were in the lab, you were to take your raw observations in a booklet like this. And I would have shown it to you, but I can't find it right now. So this is going to be your observation book. So when we do our experiment on the Bunsen burner on Monday, you're going to have the title Bunsen burner lab, and you don't need to write purpose, you don't need to write procedure. This is not the lab report. You're going to put observations. And when you make an observation, you're going to put step 1, what you observe. It doesn't have to be in a tabulated form. It usually isn't. You're just observing what you're doing in each of the steps. What you will do with this is when you then go back to make your table, this is where you're getting your reference, all right? Last year, I just had people put it on a piece of paper, and everybody was taking a picture and was just, it was kind of chaotic, the observations. I want everyone to keep their own observations in their own observation booklet. If you need to do a calculation that you're going to take a picture of, do it in the booklet. It's got a nice grid, it's nice graph paper. You can then take a picture of that little section, okay? So if you're going to do calculations, you'll do that in the booklet. So I'm going to hand that out right now, and you can call this lab booklet, or you can call it observation booklet, however you want to call it. It's up to you. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 4, 6. 2, 4, 6. 2, 4, 6. 2, 4, 5. 2, 4, 5. And 2, 4. Send them all. I'll get you. You can send the 4 back. I'll grab you one right here. Okay. Now, I'm also going to be getting you to take a picture of your apparatus. All right. Now, my plan was that you could use the lab booklet to write down the picture name. You know how your camera will give you a weird picture number, EL52673. You know what I mean, all that goofy stuff. I was going to maybe have you could write that in your lab booklet. But when you go to doing your report and you're wanting to get that image off of your phone, I realize you can easily see which one it is. It's obvious. Oh, there's that lab right there. So don't worry about writing that number into your booklet, unless you feel you really would like to. Okay, so let's now talk about the report itself. So we've done a lab, we've put our observations into the lab booklet, and now you're going to get ready to sit down and write the report. Now, I've amended my reports slightly from last year, all right? And the slight change is here in the introduction. I do want a title. Take the title right off of the sheet. I want the date. I want 2 dates on there. The date that we did the lab and the date that it's due, all right? I want that on the top of the page. And I want your name and then your partner's name in brackets. Those will be under communication. The general appearance of the lab itself falls under the communication section of the marks, okay? So you miss a bit of that, you lose a few, you lose a little piece of a communication mark. So don't miss those basic things in which the way it looks. This is one of those situations where you might say, well, that's dumb. I only put 1 date and you're going to take marks away for that? This is the classic. Find out what your teacher wants and give them exactly what they want. If you want to maximize your mark output, make it look the way I want it to look. And I just have developed a way in which I want it to look. So make it look that way. All right. This is different than last year. Last year, I would have said, just copy the purpose. But this year, I'm changing your report at the beginning. You will not just copy the purpose. You will write a paragraph that is going to be called the introduction paragraph. All right? Now, in that paragraph, it will contain the purpose. The purpose must be in the introduction paragraph. Where you put it, that's up to you. But in the introduction paragraph, you will write me a brief description of what you did in the lab and why you're doing it. So this is not simply copying the procedure, but giving me a very short synopsis of what you did in the procedure in order to fulfill the purpose. All right? In our Bunsen burner lab that we're going to do, one of the purposes is to locate the hottest part of the flame. And we're going to be taking a paper clip that we've unraveled, and we're going to stick it in various parts of the flame, and we're going to see where it indicates to us where the hottest part is. So in the introduction, you will tell me what the purpose was. That's one of the purposes. We actually have 3 purposes in this experiment, so you'll need 3 paragraphs. And you will tell me what the purpose is. You'll tell me really simply what you did to test that purpose, and in the end, why you're doing it, to find the hottest part of the flame. All right? So again, it's quite logical what we did, why we're doing it. Now, in this introduction, you will also put the variables. And I will talk in more detail about what the variables are a little later on. In an experiment, and I'm going to do it very quickly right now, there are always 3 variables. There are the independent variable. That's the thing that we manipulate as the scientist. We do this, then we change it, and we do this. Then there's the dependent variable. That's what we're looking for. In this case, that I already gave you the example, where is the hottest part of the flame? We're going to move the paper clip into different regions of the flame. That's what we're manipulating, the position of the wire. That makes it the independent variable. I'm giving you answers to this first lab. I don't know if you're catching any of this. Nobody wants to write anything? All right, that's fine. You do whatever you want. So where the wire is what we're manipulating, the independent variable. Where the hottest part of the flame is what we're looking for. That's called the dependent variable. The third variable is called the controlled variable. And that is what we keep the same each time we do an experiment. What are we going to keep the same every time we move the wire? What's going to be left constant as we do this experiment? What do you think? The flame itself, the gas amount, the oxygen amount will be left the same. Because if I change the gas and the oxygen, I will have a completely different flame each time, and my experiment will be no good. I will have learned nothing. All right? So in the introduction, you will also state the variables. I'll talk about those again. All right? So introduction, what we did, why, the purpose, and the variables. Yep. Yeah, and the dependent one is essentially what you're looking for, the effect of the independent variable, the effect of the independent variable. It's the thing you're observing, the hottest part of the flame. Where is it? Yep. The controlled variable. I believe it's later down on my sheet, but that's okay. You can write it down. It's the things we keep constant. Okay? We good to go? All right, excellent. Hypothesis. Hypothesis is an educated guess. It's what you think is going to happen to that dependent variable based on previous scientific knowledge. So again, that's going to be a little paragraph. Make reference to the purpose. The purpose will always guide you to what to think about in the hypothesis. The purpose of this experiment is to find where the hottest region of the Bunsen burner flame is. So your hypothesis is going to be answering that. The scientist believes that the hottest part of the Bunsen burner flame is going to be, well, have we done this experiment before? Does anybody know where the hottest part is before we even do the experiment? Little cheat move.
Well, you told us last year.
Yes, that's correct, I did. We did this experiment. That blue part. That blue part. Okay, well, we will need more detail than that blue part. But it does have something to do with the blue part. I'm not going to tell you what it is. So anyway, so Jillian's going to say, I believe that the... There's a cone that's exciting? Yep. Okay. I'm not going to tell you. I'm not going to give it away. So Jillian will say, the scientist believes that the hottest part of the blue flame will be at the blue part of the cone thing. I'm likely going to say, I can't visualize that. I need a little more detail. But at least that's a hypothesis, all right? And then you're going to maybe give some reason on why she would believe that, based on previous knowledge from my grade 10 class, or from the grade 10 course, wouldn't say mine. You're going to then give that explanation, okay? Sometimes your explanation on how you know it could be from experience, right? Or it could be from scientific background knowledge that you may have learned somewhere else. All right? Okay, awesome. Materials. Don't rewrite the materials, please. You're going to make a reference of the materials. You're going to say, for the materials, please see the lab sheet titled, then give me the title. You're also going to state if any changes were made. No changes were made to the procedure. If you don't tell me that any changes were made, I'm going to assume, hey, were there any changes? Again, these are communication marks. Make sure you tell me whether you made changes or not. Why do we state that there were changes made? You can do the same with the procedure. For the procedure, please see lab sheet titled, no changes were made. If I go back to the top of our example here, you'll notice here for the materials. For the materials, please see the document titled the effective concentration on reaction time. No changes were made to the procedure, all right? Let's say you're doing a lab and you're going along and you have read it, but you're just excited about science because it's so fun. And you get to the lab and you get to the end and you look beside and you'll notice, we don't have nearly what they had. What's going on here? And then you ask me and I say, well, what did you do? And then you describe it to me and I said, well, that wasn't the procedure. You changed a step somewhere. You'll panic, you'll freak, and I'll say, calm down, it's okay. You're just going to tell me where your procedure is different. And you're going to write a report that's slightly different than everybody else's, okay? So if you make a change, you're going to simply tell me what you did differently, and then I'll just evaluate your lab based on that, right? Okay? Labs have a degree of correctness, but there's many things that can be correct in a lab. There's many ways to be correct in a lab, okay? All right? Okay, so please make references, and please make it look like that, right? Make it look exactly the way I want it to look. All right, diagrams, this is new. A labeled picture of your assembled apparatus. So once you get your apparatus assembled, or sometime during the lab or at the end, put out all the stuff that you used, get it into a frame and take a picture of it, all right? Years ago, we used to have diagrams, right? Please draw a diagram of your apparatus. I hated it. I was terrible at drawing the diagrams. But now with your phones and the cameras, take a picture of your apparatus. And then you're going to label them, all right? Now, there is a way to put nice label arrows, right? But what you can do is, an easier way, underneath the diagram, this just came to me yesterday because we were doing it with the college kids, the college class. Going left to right across the picture, just list the apparatus, right? So starting on the left, if the first thing you've got furthest on the left is like the tongs, the crucible tongs, then put crucible tongs. And then as you move to the right, just label them, okay? That's going to be, I'm going to be testing you on whether you know your apparatus or not. That's how that's going to kind of work, okay? So you can do a fancy label thing, but you don't have to. You can just go left to right, you know, and then just list it down. as it works. Okay, notice here, please do not take any lab selfies. My grade 12 university class last year, Taylor, who else was in that group? Taylor Parnham and Trache was in there. Jeez. Every lab involved, somebody's face behind the apparatus. Don't do that. Please. If you do happen to get someone, in the background, don't worry about it. But please don't pose with your lab equipment. It's not like an Instagram thing. Hey, doing the lab. Woo, love and science. Anyway, just take a picture of the lab report. What I want in a lab report is for it to look professional. Because when you go to university, and if you continue on to graduate school, when you do reports for your professor, they're to look like professional reports. And that's what I want this to look like. I want it to look professional. Okay. All right. Observations and calculations. So observations and whoops, where did I went too far? Most observations include quantitative and qualitative observations from your experiment. Raw observations are to be logged in the booklet. This data or observations should be placed in a table whenever possible. Tables are the way to go, all right? Please, in your observations, only write what you see. Don't write what you think. Sometimes we get carried away and we know what a substance is. We know what that is. And sometimes we want to write that in our observations. Let me give you an example in this lab. We're going to be dealing with the paperclip and we're going to put it in the flame. Does anybody know what the paperclip's going to do once we get it into the flame long enough? What's the reaction of the paperclip to the heat of the flame? What's it going to do? Put a piece of metal in a flame, leave it there long enough. What eventually happens? It would melt, but we're not going to get quite that hot. So we're not hot enough to melt. So what's it going to do before it melts? It's going to turn red, right? It's going to glow. It's going to turn red, right? Now, many students will write down in their observations, it was hottest here because it turned bright red. Now, to state that it's hot is actually a conclusion. You've made a decision about what the glowing red is. Please do not put conclusions in your observations. Put conclusions in your conclusions. So if you tell me that it's hot because it's red, I will say no conclusions here. -1/2, right? We'll take marks away. Yep. In the observations. Yes. Observations are really easy. Observations are truly a no-brainer. To state that it's hot means you had to think, oh, that's really red. It must be hot. When you do an observation, you don't think bright red very quickly. Quickly bright red, right? That type of thing. That's it. Just tell me what you see. Observations are easy. There's no thinking involved. As you're going along in your book, in your rough book, you could go bright red, hot, exclamation point, but that's not going to go in your observations. That means you're already thinking about your conclusions. And that's what a lab booklet is about as well. You might have a little thing on the side, some conclusions, some ideas, things you're learning as you go along. That's okay to put in your lab booklet. That's encouraged. But don't put conclusions in your observations. Just put what you see. Okay? All right? Yep.
So you tend to like something hot?
Yes, that's right. You put what you see, don't put what you think. Right? You might think it's hot. We haven't done any tests to state that something glowing is hot. Has anybody ever tested that before? How do you know that a glowing hot piece of metal is hot? What would we have to do? We'd have to touch it. Don't do that. Or maybe just put it against your tongue. That'd be fun. Step 5. Now put the glowing thing up against your tongue. That'd be fun. No, we can't do that. So we don't know that. So we might know it from previous, some when you were a kid. Those sparklers, those killer sparklers. Let's get the sparklers out. Every time you get the sparklers out, some kid is crying. Anyway, I digress. Yep.
So you don't really know, right?
Because we haven't tested that it's hot? You're right. That's correct. Yeah. Oh, well, if you'd like to touch it on your tongue, go ahead and do that and test that out for you. How about I tell you right now, by the way, if a piece of metal is glowing bright red, it's hot. I've tested it. So you're getting that knowledge from me. What do you got to be that way, Abby? Cheapers. Okay, let's keep going. If you're dealing with numbers, and this will come later on, if you're dealing with numbers, units go at the top of the column, all right? So if I go back up to this, units only appear once at the top of a column. Here we've got reaction time for my example lab. Seconds in the top, just numbers in the column. When we get to the second half of the course and we start doing more numerical stuff, this will become important. If you put seconds, no, that's not the proper way to represent that. The name, the units, and it's at the top. Okay, excellent. Let's move on here. So, again, for calculations, you can take a picture, et cetera, et cetera. Conclusions in lab analysis. Conclusions also are easy. These are kind of like answering any question that I ask you, say, to write an answer for, kind of like our MSDS sheet assignment, which I'm currently marking through. I like you to restate the purpose first, all right? Because that focuses your mind on what you're going to answer. The purpose of this experiment was to locate the hottest part of the Bunsen burner flame. Boom. Write it out, okay? That focuses your mind on what your answer is going to be. The second sentence is the concluding statement. Now, I got into an argument with an English person stating, no, you must put the concluding statement at the end. And then they said, that's why it's a conclusion. And they didn't say duh, but they thought it. And I felt bad because I'm not good at English. But I like you to put the concluding statement second, because I want you to state what the purpose was, and then I want you to state what you found. It was found that the hottest part of the Bunsen burner flame was at the blue thing, edge, cone thing. Anyway, no, you'll have a better answer to that. I don't want to give it away. Where you found it to be. So, state the purpose, state what you find. The last part of the sentences will be giving me the evidence. This was known by the fact that the wire, when placed at such position, took a long time to glow, and when it was placed at this position, it was glowing very, very quickly soon afterwards. Give me all the evidence that you have. Don't just give me one piece of evidence and say, hey, that's that. If I'm getting you to do a procedure in the lab, I'm getting you to find evidence, and I want you to use the evidence in the conclusion. Now, some of you might say, this is crazy. I wrote all of the evidence up in the observations. It's right there. You mean I've got to write it again in the conclusions? And there are many students, and I was that particular student. I was that student that would say, it was found that the hottest part of the Bunsen burner flame was at the blue cone thing, and as you can see from the observations above. And I'm going to say, no way. I'm not going back up there to look at those observations. I'm not going to make the logic for you. You need to tell me again. And you're going to find you're writing the same thing over again. But that's very important. Like I said, it's like you are a lawyer and you are going to make concluding remarks to support your client. And when you make your concluding remarks, you're going to restate all of that important evidence so that the jury thinks they're innocent. And my job is to read that and say, yeah, I believe it. I am not going to put my finger at the Bunsen burner flame at that position because it's really hot, right? So you're going to sell it to me, okay? All right? Excellent. Okay. And for each purpose, you've got to have a concluding statement because each purpose has a conclusion built in with it. Error analysis. This is the part of the report that students absolutely hate. Because up to this point, the report's quite logical, right? You're going to tell me why you did it and what you did and the variables. That can be tricky. Students struggle with that. hypothesis, that can be tricky because you got to think about why you're going to make the guess. But when it comes to the rest of it, observations, tell me what you see, make references, conclusions, what's the purpose, what did you find, give me the evidence. It's a no-brainer. You're just filling it in. This is the trickiest part of the lab. This is where your application marks come in. By the way, the calculations and conclusions are your thinking and inquiry portion of the lab. The way the lab looks is communication. The knowledge is the introduction and hypothesis, because it takes, for you to understand. The thinking and inquiry portion of the lab is the conclusions and the calculations, because that's where you've got to, synthesize what you've learned. And this is the application part of the lab, okay? Every time a scientist makes an observation, there is always error built into that observation. And when I say error, I don't mean mistakes. Mistakes are made when you don't do something properly, all right? So I'm not talking about mistakes here, but I'm talking about situations that arise when we measure something that prevents us from getting the correct answer, from getting the correct observation, okay? I'm trying to think of an example of an error analysis that I could give you here. I'll use the Bunsen burner as an example. All right, so I got a Bunsen burner here. This one actually doesn't work, so I'm not going to fire it up. Another purpose of the experiment we're going to do on Monday is to compare a flame of the Bunsen burner when the air is shut off and there's no air getting to the flame, and when the air is turned on, okay? We will get two completely different types of flames under those two conditions, and that's one of our purposes, right? On versus off. And many times when students do this experiment and they turn the air off, what I'm doing here, and I'll go over this with you on Monday, I'm turning the barrel and I'm bringing the barrel down, and what that does is it closes these windows, which prevents the air from getting in with the fuel. So in order to turn it off, you turn the barrel down like this. All right. Sometimes the base, where this thread is, gets all corroded, and I can hardly turn it. And it actually prevents me, or prevents the student, from turning it down all the way. And so you turn it as far as you can, and you light the Bunsen burner, and you start doing your experiment. But due to the Bunsen burner itself, you couldn't turn it right to the bottom, which means there was some air getting in. That's an error. That's a problem with the equipment. There was nothing you could do. I didn't tell you to watch for it, so you just kind of went through the experiment, but a little bit of air was getting in. So the error is that we couldn't cut off all of the air supply when we wanted to study the flame with no air. That's a problem with the equipment. That's an error. Let's talk about the types of errors, and then we'll come back to this example. So the error analysis gives reason as to why your result might be incorrect. There are two types of errors that can exist: systematic error and random error. So systematic error is an error that results in a consistent bias in the measurement. That means it's always off by the same amount. I'll talk about that in a moment in more detail. It is often called a calibration error or an instrument error because it tends to be due to a malfunction in a piece of equipment like a Bunsen burner or a scale. Using proper techniques, calibrating the equipment, and employing standards, in other words, cleaning equipment up, making everything perfect, and using standard masses, I'll talk about that in a moment, help reduce this effect. Do not use errors that can be humanly avoided. In other words, if you've made a mistake, that's something different, right? If you have to read a volume and you say the error is in the volume of the graduated cylinder because my partner doesn't know how to read a graduated cylinder, that's not an error. That's something where you say, hey partner, let me show you how to read a graduated cylinder. I will inform you and teach you, then they read it properly. So errors are built into equipment. They're not mistakes. Random errors result in small variations in measurement due to randomly changing conditions, such as contamination of reaction vessels, impure reactants. You can also have it as an error with a scale. Let's say you have a scale and someone walks by and moves the air over top of the scale, your scale value will change. So that air movement could actually change what the value is. That would be a random error because it's fluctuating because of air pressure changes, okay? You can have human error when it comes to random error, but use this rarely, all right? Human error is something like reaction time. Let's say we're using a stopwatch in physics and you're wanting to time something quickly and you're dropping a mass and your partner says, go, and then when it hits the ground, stop, right? That's a tricky thing to do. You know, maybe if you're an NHL goalie, go, stop, perfect. I'm awesome. My reaction time is great. And maybe you're, I don't know, not an NHL goalie. And your partner says, go. And you say, huh? What? Oh, yeah, okay, go. Hits the ground. Oh, it's the ground. Stop. That wouldn't be a very good measurement to use. There'd be a lot of error there. That could be a human error. Actually, the way I described it, that's not a human error. That's just, come on, man, pay attention. Okay. And then doing your best. Doing the best you can, there will always be off. You'll always be off a little bit. And sometimes you'll be short, sometimes you'll be too long, and it'll be random on how much you're off. That's a random error. So due to our humanity, running a stopwatch is difficult, okay? Now timing something for 30 minutes doesn't have the same amount of human error. Go, all right, do your thing, 30 minutes, stop. That little reaction time on top of 30 minutes is nothing. But when you're dropping something for like 1.25 seconds and your reaction time is 0.5 seconds, you've now added a big chunk. So it also depends on how short the time is. Don't use human error very often. Yeah, the volumes might be incorrect due to human error. And I'm gonna say, what, you can't read a graduated cylinder? It's not like a stopwatch, people. So you know what I mean? Don't say human error just for reading a cylinder or reading, you know, really, stopwatch would be the only thing, right? I guess if you were colorblind and you had to write down colors, you'd have a situation like that. Mr. Frayne is colorblind, actually, by the way. He went to Western as well. And whenever he would do an experiment that involved color, what do we got here? What's color here? Oh, it's not done yet. Okay, keep going. Right? Anything that involves colors, that would be human error. He has no control over that. I guess bad eyesight would count as human error, right? So if you were trying to, you know, estimate a distance of something that's far away, if you have bad eyes, you theoretically could have human error because you haven't, you know, it's a restriction of your body. Okay. Equipment error, if it's set up incorrectly and it's really wobbly, you know, it might have that because it can wobble back and forth. Environmental error, that's typically the case. Humidity, temperature, light sensitivity, etc. Okay. So how do you do an error analysis? And this part on the very bottom is kind of important here. So when you do an error analysis, you must have these steps in it. You must state what the error is. The Bunsen burner could not be turned down completely due to corrosion of the base. That's a statement of the error. And then you've got to write down how it would have affected your observations. Well, you tell me. If we've got a flame that has lots of air and it's burning nicely, and I have a flame that I want to shut off with no air, but I can't shut off all the air, that's going to change my flame. It's going to have air, and I want it to have no air. So you'd have to guess on what it's going to do to that flame. Does anybody know how a flame that has air going to it is different than a flame that has no air? Does anybody know, maybe from previous experiment or previous experience? If we've got no air going to the flame, we can see the flame, and we've got some air going to the flame. How does the flame look different? Any ideas? Lots of air. You could think of the same as if you've worked with a torch. If you've ever worked in a shop with an acetylene torch, you fire up the torch and then you add the oxygen. How are the flames different? It's the same scenario. It's exactly the same. Yep. Yeah, you had an idea. Come on, give it to me. Yeah, you could have a different size flame. That's correct. Which one would be which? Any ideas? Abby? It's wiggly. It's big. Do you know what the color is if it doesn't have a lot of air getting to it? Sorry? Orange. And when we've got air going to it, what's it look like? Blue. All right? And it's more stable. Okay. So if I can't crank this down, how's the flame going to appear compared to what it should be? If I can't get rid of all of the air, and I want to study that thing with no air, how's the flame going to look? I've got some air in there that I don't want in there. How's it going to look? Can't get rid of all the air. It's unfortunate. I can wait. I've been doing this a long time, so it doesn't freak me out when nobody puts up their hand. Mitch, what do you think? I can't get rid of all that air. How's it going to look? It's still going to be orange, but there's going to be a little bit of air coming in. So what else? What other property is it going to have in there? It'll have some blue. It'll have some blue that you didn't want to study, right? So it'll be bluer than it should have been. Now that's the effect. We can't crank it down, can't stop all the air. What's the effect? This will make the flame bluer than it should have been. So we've now talked about what we saw that was incorrect. The last thing I want you to do is tell me how to fix it. Now, it says there at the end, how to fix the error. If you were to redo the experiment, how could you eliminate this? And right at the end it says, be practical and relevant. I should have put that in bold. Many students will just say, get a new Bunsen burner. I'm going to say, no, not enough money for that. Not doing that. Many times if we talk about scales, many students will say, get a high-tech scale. Or say, okay, great. I'll just go to the high-tech scale store and buy a high-tech scale. What are you talking about? What's a high-tech scale? That's not practical. So using stuff that you might find in a laboratory or maybe around the house, if you were doing this lab, you could talk about how to fix it. So let's say we get to this point, I can't close it down. How could we solve this problem? What could we do? Jackson, what do you think? You look like a handy guy. Here it is right here in front of you. I can't go any further. There's corrosion all over the place. What could I do? I want to stop the air from getting through here. Okay, excellent. Be more specific than that. That's an excellent example, but you're around the house or you're in the lab. What could we put over it? Tape. Awesome. That's exactly correct. And I'm a fan of a particular type of tape. We're Canadians. What type of tape do we love to use? Scotch tape. Drop the, what's that? Duct tape. Duct tape. Use duct tape. No? There used to be a show back in the 80s, 90s called the Red Green Show. Anybody? Weird old guy with a beard, and he would always talk about using duct tape to build everything, fix everything. It was hilarious. We could use duct tape. Sure, awesome. That would be a great practical thing to do. Get some duct tape, tape up the holes, do that part of the experiment, and then untape it. What else could we do? Some other handy people, what else could we do? There's corrosion around here. How would you fix that? Anybody likes working in the shop, fixing the cars, that type of thing? Anybody? What could you do? Well, I would take it off, and then I would get a steel brush. You know the steel brush is, right? And I would clean it off as best I could. I might put a little bit of oil on it, and I might try to get that to work. That's a practical thing that could be done. All right? So when you're suggesting a fix, please be practical. Get a new one. No, I'm not getting a new one. We're not going to do that. Okay? All right. So before we talk about the mark breakdown, I want to just do one more little example of the error analysis. Notice here, I've added another section. So here it says, state what the error is. Oh, I forgot. There's a second part to it. Tell me the type of error. Is it systematic or is it random? You can use equipment error. You can use environmental error. If I can't turn this thing down, that makes this a systematic error because it will always make the flame too blue. It can never be too yellow. So if the error always makes the effect always to one side and never varying back and forth, it makes it systematic. If you've got a scale that the numbers keep changing, you know how sometimes you use those scales and that last number keeps going 5, 4, 5, 4, 5, 4, 5, 4, 5. Get the idea? That means there's something random happening in there. Something's causing that scale reading to fluctuate up and down. So it's fluctuating up and down. This will always be too blue, therefore it's systematic. So I need you to tell me what it is. Okay, so let's say that we have an experiment here. The purpose is to determine the density of aluminum and plastic and wood. And actually, I in the past, I've kept a little container of that in here, but I've put them away because another class needed it. You would have used them in grade 9, the little cubes of aluminum and plastic and wood. Let's say we wanted to determine the density. So we would figure out what the volume is, measuring the length, side, and width, and we would measure those. And then we would take its mass on a scale. The independent variable is the density, is the identity of the material being used. Each experiment, we're going to change. We're going to go from aluminum, do the experiment, to plastic, do the experiment, to wood, do the experiment. So that makes it the independent. We are changing the identity of the material for each trial. The dependent is the density itself. That's what we're looking for. In most purposes, you will be able to find the independent and the dependent, all right? To determine the density of aluminum, plastic, and wood. You can see there, that's what we're changing, the independent. What are we looking for? The density, the dependent. Typically, the dependent and independent will be found in the purposes. Controlled variables, the equipment being used to make the measurements, the same scale is being used, the same ruler is being used. All right, so an error analysis for this. What could have happened? This is what I would call a weak analysis. The scale was off what it should have been. So let's say we put the scale and we read it and the number was too high. The scale was off. This is an equipment error. This will affect the results. Get a new scale. Absolutely unacceptable. Doesn't tell me what's off, doesn't tell me how it affects the results, and getting a new scale is not going to be the case. A slightly better one. The scale reading was too high, because let's say it was calibrated wrong. You know how sometimes if you've got a bathroom scale, it gets off from being what it should be at 0, so you recalibrate it. Let's say that was the case here. The scale was too high. This is a systematic error due to problems with the equipment. Nice. This will make the masses too big and change the numbers in the density equation. Okay, that's okay, but it's not very specific. To fix this, a more high-tech scale connected to a computer could be used. Again, high-tech scale, really? That doesn't necessarily fix it if it wasn't reading 0 at the beginning. Not great. So here's a better one. When the scale was tested with a 200-gram standard, so we put a standard mass on, its reading was 202.5 was measured. So it's reading too high for the 200-gram standard. This is a systematic error due to the fact that the mass will always be too big. This means the scale reading is too high. Excellent. So we've got what the error is. According to the equation D equals m over v, which is our density equation, if the mass is too big, then the density will be too big as well. So if my number for m is too big, then my answer will also be too big. because the number on the top is going to be too large. My answer is going to be too big. This could be minimized by testing the scale with known masses that is close to the measured mass and subtract that off from the value. So we could do a test mass, see what it reads, see how far off it is, and subtract the number off of what our mass is, and that will then bring us to what it is. So we need you to be specific with the error analysis. Okay. And I know this has been a long talk, but in order to get the labs the way I want it, I do need to go over this. Last, I want to talk about the way I'm going to grade them. And this is going to be different again. This is going to be only for formal lab reports, and this is going to be new for me. I'm going to level the formal lab reports. Now, I know many of you do not like the leveling system because the leveling system pegs your marks, right? You get a 4+, and you go from, say, 4++ or 5 to a 4+, and it's a big jump, and that's even greater than -0.5. Oh, yeah. Oh, I had this debate with my son. He absolutely hates leveling, but I am going to level the formal lab reports. I'm going to use a leveling system based on a top mark of 5, which is like a 4++. And I'm not going to have pluses and minuses. There's just going to be halves. This is actually what they call the grade point system in the United States. If you have a grade point value, it's essentially out of 5. So if you have an exceptional error analysis that is absolutely beautiful and perfect, 5. Now that's a difficult thing to get because it does have a lot of detail to it. If you have a good, you've got a 4. That gets you 80% for that. Oh yeah, Abby is losing her mind right now. It is awesome. My son gave me the same look on his face when I said I was going to use this. Now you might say, why are you doing this? In the past, I looked for 5 things in the error analysis. Did you tell me what the error was? Did you say what type it was? Did you say what the effect was, right? Really detailed. And did you give me a good fix? And there were many error analyses that had all those components in them, but they were to the most minimal explanation of what that particular thing could be. So I ended up giving them a 5 out of 5, but it really wasn't a 5 because it had all the components, but it didn't have them at their best. You see what I'm saying? Yeah, Abby's still hating it. That's why I'm addressing this directly to her. So I will be making decisions. You may have all 5 components, but if they're not satisfactory or they are just satisfactory, you get a 3. And that allows me to distinguish between the people who are exceptional at thinking about error analysis and those who are either satisfactory or good. Yes? No. Each category, communication will get a level. Knowledge will get a level. Thinking and inquiry will get a level. Application will get a level. Communication is going to be how the lab looks. Is everything underlined? Do you have all the units in the right place? Did you, did you put the title and you put the name? The overall appearance. Grammar and spelling. Proper, and I can check spelling because it comes up red on Google Docs, right? Did you fix all those things? Knowledge is going to be the introduction and the hypothesis. Is it full? Did you have a proper explanation? Thinking and inquiry is going to be the conclusions and the calculations. And application is going to be the error analysis. Yes?
So let's say in this case you felt like one thing wrong, you're dealing to 80% then?
I haven't decided exactly how I'm going to deal with that because this is the first time I'm going to run it. So no, I'm going to keep 0.5s, right? And I'm going to come up with a scenario where maybe you need to make 3 mistakes to move you to the other one. I haven't figured that out yet. You shouldn't be making spelling mistakes because the red comes up on Google Docs. You should be fixing those. You know, capitals at the front of the sentence, please. Don't type it like you're typing a text, right? Yep.
So like the purpose of that is not going to have your
the introduction and the hypothesis will go in the knowledge. So if you don't have the purpose in the introduction, you haven't fulfilled it. So you will lose from 5. But it is. I'm grouping some things, and I'm leveling them instead of subtracting little marks. You see what I mean? Well, no, I'm reading it and I'm asking myself, is this excellent? Is this an absolutely beautiful thing? Or is this just average? And I'm imposing the mark like an English teacher would do on an essay. Yep.
What if it's only 100, like not 80? It's better than 80, but not 100.
I'm using halves as well. It could be 90. Yes. Yep. That doesn't exist anymore in formal lab reports. That's what leveling is, folks. That's the way that goes. That's how you level things. That's how it's done. Any other awesome questions? There will be no 99. But there will be a 90. Yes. Yep. Okay. I'm going to stop recording here because I think we've covered most things. YouTube,